Ideal gas law. P for pressure, V for volume, T for temperature, and again, as in all the other laws, T has got to be in Kelvin. And then we have N and R. N stands for the number of moles, and R is simply a constant that will be the same in every problem depending on our units. The key for R is that, notice I have 4 units here: atmosphere, liters, moles K, or kPa, liters, moles K. That's so that depending on which variable I don't know, all the other units will cancel out except the one. So if I'm in atmospheres, I'm going to use 0.0821. If I'm in kPa, I'm going to use 8.31. There are other ones, if I wanted to do my pressure in millimeters of mercury, then I'd have a different R for that. Or if I was in pounds per square inch, I could have it. But the book likes to use 8.31 for the most part, and sometimes you'll see 0.0821. I tend to like this one because it goes with the STP, standard temperature and pressure. Yes?
What did you say R was?
R is just a constant. So it's always going to be this number, the 0.0821, if I'm in atmospheres for my pressure, or it's going to be 8.31 if I'm in kPa. And it could be in other ones if I had other units, but generally speaking, these are the two we would use. Either 0.0821 atmosphere liter per mole K, or 8.31 kPa liter per mole K. And the basic difference between this one and the other laws is the N, the number of moles. So that I can actually think about, hey, you know what? If I had a container and, my volume didn't change, like a can or a bottle, and my temperature didn't change, but I put in twice as much gas, 2 moles instead of 1 mole, say, shouldn't I expect the pressure inside the container to change? Because there's now a whole bunch more of them. That's the idea behind the ideal gas law. And of course, other things can change as well because, I could keep the pressure constant, but if there's more of them zipping around, then, I've got to change something, so the volume would have to change or the temperature would have to change. Something would have to change if I have more moles. So, number 1 here, calculate the volume of 1 mole of a gas at STP, standard temperature and pressure, using the 0.0821 atmosphere liter mole K. So, first of all, N is 1 mole. N is the number of moles. STP, so my temperature, 0 degrees Celsius, which of course means 273 K. And my pressure is 1 atmosphere. These are what STP is. All right, so now PV is nRT, or if you want, V would be the nRT over the pressure. Solve for the volume. So 1 mole times the 0.0821 atmosphere liters per mole K. My temperature, the temperature 273 K, and then divided by the pressure of 1 atmosphere. Now note, and this is why R has all those different units. Here the mole canceled with that mole, the atmosphere canceled with that atmosphere, the K canceled with that K. The only one that's left is the L, which are the units for volume. Now, you multiply all of that out, and you end up with 22.4 liters. And if you have a calculator out, you can go ahead and see that you actually get that yourself. But if you go back to our stoichiometry unit, our mole unit, what did we say for all gases at STP? 1 mole was 22.4 liters. That's where the 22.4 comes from. It comes from the ideal gas law. And of course, if I had had more than 1 mole here, then I would have had more than 22.4 liters of that gas. So that's using the ideal gas law. All right, underground cavern contains 2.24 times 10 to the 6 liters of methane gas, which is CH4, at a pressure of 1495 kPa and a temperature of 315 K. How many kilograms of CH4 does the cavern hold? This is really the big difference of the ideal gas law versus the other laws. I can now find out how much stuff I've got, not just in liters, okay, not just in a temperature, pressure, whatever. I can actually, how many grams, how many kilograms of this stuff do I have? So, just like before, okay, PV equals nRT. Now, I want to get to kilograms. Kilograms means, hey, if I knew the number of moles, then I can find the number of grams. Well, remember, N is the number of moles, so basically, again, doing a little solving, N has to be PV over RT. So, pressure, there's my pressure one right there. There's my P. This is my V. There's my T. So my pressure, 1495.8 kPa. My volume, 2.24 times 10 to the 6 liters. Now, in this case, I'm going to use 8.31 for the R because that's the one that's done in kPa liters per mole K. And then my T was 315 K. So again, here's my P in kPa. There's my L, using the 8.31 this time, kPa liters per mole K. And just as I mentioned, here the K's will cancel, there the kPa's will cancel, the liters will get canceled. The only thing I'm going to have left are the moles. And so, multiply all that stuff together, and I get, looks like 128, well, actually 1,280,000 moles. Okay, but I want to know kilograms. Well, of course, CH4, that's 16 grams per mole. Again, go back to the previous unit. Carbon's 12, 4 hydrogens, that's 16. Everything on the periodic table is for 1 mole, so I have 16 grams per mole. So if I take my 120, actually, if you think about it, 1,280,000 moles times 16 grams per mole, I'm going to end up with that many grams. Okay, now how do I get from grams to kilograms? Every kilogram has how many grams? That's right, 1 kilogram divided by 1,000. And so all I have to do is take off 3 zeros. And so 20,480 kilograms is what I'm going to end up with. Now that's a lot of kilograms, but we are talking about an underground cavern, so that could be quite large. But here's the really useful thing about the ideal gas law is I could turn in so much gas, not at STP, but at some temperature and some pressure, and figure out how many actual grams, how many kilograms, how many molecules, if I want to know molecules, is there. Okay, number 3. When the temperature of a rigid hollow sphere, the rigid just means it's fixed. It's not like a balloon that could expand, so it's rigid. It's going to stay the same volume. Containing 685 liters of helium gas is held at 621 K. The pressure is 1883.4 kPa. How many moles does the sphere contain? So again, there's a T, there's my P, here's my V. PV equals nRT, or, because I want how many moles, number of moles is going to be PV over RT. So start plugging them in. 1883.4 kPa. Volume 685 liters. My R, again, in this case, I'm going to use the 8.31 kPa liters per mole K. Actually has 4 different units. And then my T, 621 K. And this one comes out to be 250 moles. And of course, if I wanted grams, then I could do like I did in the previous problem and change my moles into grams. Or if I wanted molecules, actually helium, since it's a noble gas, would just be helium atoms. So I would go to atoms and go times 6 times 10 to the 23rd atoms per mole. Any questions? Again, as we're going along here, I would use your calculator, see if you come up with the same thing. Make sure that you are doing it correctly. Okay, number 4. A child's lungs can hold 2.2 liters. How many grams of air do her lungs hold at a pressure of 0.997 atmospheres and a body temperature 37 degrees Celsius? So here again is my P, here's my V, there's my T, and I want to find out grams. So just as in the previous problem, PV equals nRT. I'm going to solve for n, the number of moles. So pressure 0.997 atmospheres. Volume 2.2 liters. This time, because I'm in atmospheres, I'm going to use the 0.0821 atmosphere liter per mole K. And my temperature, now that's 37, so my temperature 310 K, 37 plus the 273. This comes out to be 0.0862 moles. Now, it says up here, use a molar mass of 29 grams. Remember that molar mass means the mass of 1 mole. So, I'm going to take my moles times 29 grams per 1 mole. Kind of like one of our mole problems. And we end up with 2.499 grams. Or, if you want, 2.5 grams of air. Or, excuse me, 2.5 grams, of air. So that's the actual mass of the air inside the child's lungs, 2.5 grams. Questions? All right, last one. What is the volume occupied by 20 grams of a gas at 15 degrees C if the pressure is 81.8 kPa, use a molar mass of 34.43 grams? Now, first thing is, hey, they gave me grams. Change that to moles. So I'm going to take my 20 grams, use my molar mass, so 1 mole over 34.43 grams. That comes out to be 0.581 moles. That is N. N is the number of moles. And then, of course, here's my P. Here's my T. And it wants to know what the volume is. Every one of these is going to give you everything except one. Solve for the one that's missing. So in this case, PV equals nRT. I want to know volume. So my volume is going to be nRT over the P. So there's my number of moles, 0.581 moles. My R, again, since I'm going to be in kPa, I'll use the 8.31 kPa, liter per mole K. I have my T. 15 degrees makes it 288 K. 15 plus 273. And then all of that is going to be over my pressure of 81.8 kPa. So that the kPa's, the moles, the K's all cancel out, and I'm left with just liters, and it turns out this will be 17.0 liters. Any questions? Now again, one last little thought. When we get to the test, you're going to have all the equations at the top of the page. You got to figure out which one to use in a given problem. Well, in this particular case, for the ideal gas law, if they tell you so many grams, or they tell you so many moles, or they want to know how many grams, or they want to know how many moles, that's the clue that tells you, hey, I want to use PV equals nRT. That's the big clue, because they're asking about grams or moles. The other thing, of course, is notice I have 1P, 1V, 1T. In all the other gas laws, I had 2 of something, 2 P's or 2 T's, solving for one of the things I didn't know. Here I've just got 1P, 1V, 1T. So that's the second clue to use the ideal gas law versus using, say, the combined gas law, where I got 2 P's, 2 V's, and 2 T's to worry about. All right then.